Okay, so we're in section 3.2 now, analyzing graphs with the second derivative. Before we can get into the part of the section here where we're looking at any graphs, we first need to talk about what a second derivative is, because that's not something that we have used yet. So in chapter 2, we spent a lot of time developing the idea of what a derivative is. So given some function f of x, we use this notation f prime of x to represent that derivative of x, or of f of x. But since f prime of x is a function in its own right, it may have its own derivative. So if you take the derivative of a derivative, you get what's called a second derivative. And in that context, it kind of makes sense to refer to f prime as the first derivative of f. So now we have a concept of a first derivative and a second derivative. Notationally, this describes the definition we just gave. So our second derivative will use the notation f double prime of x. It's got two of those prime symbols. And what it means is the derivative, so d dx, of the first derivative, f prime of x. Other notation that we might use is given down here. So if we use a variable like y to represent our function, then we could call it y double prime. Or in Leibniz notation, we might use something like this. Remember, the first derivative looks like dy dx or df dx, depending on what we're labeling our function. In Leibniz notation, the second derivative looks like this. It's got these 2's that look like exponents, but that's not technically what they are. So make a note of that notation, and that's going to show up every now and again. So what I want to do is get a little bit of practice evaluating second derivatives for a couple different types of functions. Starting with this first one, we have a polynomial. Y is equal to that polynomial. So to find the second derivative, you're going to need to start with the first derivative, y prime. Okay. So using my power rule and kind of the rules that we've come up with and have been using for a while now, this becomes 35x to the fourth minus 12x squared plus 11. And that constant goes to 0, so it's gone. To get this second derivative, y double prime, I'm just taking the derivative of the function I just got. So I'm taking the derivative of the first derivative. 4 comes down, it'll multiply to this. That would give me 140x cubed minus 24x, and then the 11 here is a constant, so that goes to 0, and this is what I'm left with. Okay, that's my second derivative. That's about as simple of an example as we can give, because polynomials, as you know, are the easiest class of functions to differentiate. But we have another example over here where the function is a little bit different. F of x is x squared times the natural log of x plus e to the 5x. So I start with my first derivative, f prime. And I have a product of two functions here, so I'm going to need to use my product rule. Derivative of the first function is 2x. Leave the second function alone, plus the first function times the derivative of the second function, 1 over x. That's my product rule applied here, plus e to the 5x. I need its derivative from the generalized exponential rule that we talked about previously. That would be 5e to the 5x. We can simplify this a little bit by doing some cancellation here. So I'm going to get 2x natural log of x plus, this would just be x after canceling, plus 5e to the 5x. So that's only the first derivative. I now need to take another derivative for the second derivative. What do we get here? Well, once again, I have a product of functions, so I need to use my product rule. Derivative of the first function would just be 2. Leave the second function alone, plus the first function times the derivative of the second, the derivative of the natural log, 1 over x. And then here, plus x, that will become a plus 1. And then here, I'm going to get 5e to the 5x times another 5 from the derivative that I would take for that exponential function. That becomes plus 25e to the 5x. Okay, some simplification that can happen now. These x's cancel. 2 times 1 is just 2, but then I have a plus 1 here as well, so these two terms are going to combine and give me a 3. 2 natural log of x plus 3 plus 25e to the 5x. And that would be my second derivative. Okay? There's lots and lots of examples we could do, but since we've already practiced taking derivatives plenty up until this point, it would kind of feel like just more of that. So we're going to start moving into some interpretation of the second derivative. So as we've seen so far, if you're given a function f of x, the first derivative of f gives you some useful information about f itself. So we know, for example, if f prime, your derivative, is positive on some interval, then the original function f is increasing on that interval. If f prime is negative, then the original function is decreasing, and if it's equal to 0, then you have a horizontal tangent there. So that's information we've been using. From that information, we got the first derivative test, which is a method of determining local maximum and minimum values of a function by using that first derivative. Now what we want to do is shift our focus to the second derivative. What could the second derivative tell us about a function? Well, it turns out that the second derivative is related to a concept called concavity. So the intuitive idea of what concavity is if you have a graph of some function y equals f of x, that graph might have some curves, parabola. You can imagine a parabola. We'll show you some pictures on the next page. Kind of curves, and those curves will either open generally upward or downward. And so concavity is sort of a description of that. If the function tends to curve upward, we say that it's concave up, or if it curves downward, we say that it's concave down over whatever interval that's occurring on. So here's some actual examples to illustrate that. Here we have a function that's concave up. It opens upward. Here's a function that's concave down. Notice it's a little less symmetric than this one is. It seems to be pretty steep here, and it goes out like this. This is, in fact, a logarithm that's been shifted around, but it's still concave down because it has to be one or the other. It does not look like it's opening upwards, right? So that's a great way of understanding concavity just by looking at a graph. Which direction is it curving? But that's not a very mathematical approach or a definition for what concavity is. So we actually have a more precise way of defining concavity, which is going to lead us into some of the results that we use in this section. In particular, notice here we have a concave up curve. And if you notice, if you look at any point on that part of the curve that's concave up and then find a tangent line to that point, the blue curve lies above those tangent lines. You notice the tangent lines are going underneath the curve, except at the point where they touch the curve. So something similar happens over here. If we have a curve that's concave down, then it's curving away downward from its tangent lines. So it's going to lie below its tangent lines, at least on that interval where we have concave down. So we're going to use this actually to define concave up and concave down. A curve is said to be concave up on some interval AB if the curve lies above its tangent lines on that interval, and it's said to be concave down on an interval AB if it lies below its tangent lines on that interval. So that still doesn't reveal right away what the relationship between concavity and the second derivative is. But let's use these pictures as sort of a guide. So remember, first of all, that the second derivative is the derivative of the first derivative. And we can interpret any derivative as a rate of change. So we can think of the second derivative as the rate of change in the first derivative. And we use rates of change to determine whether a function is increasing or decreasing, things like that. So if you think about this first image right here, looking at these tangent lines, the first derivative, f prime, is going to give me the slope of these tangent lines. But you can see from the picture that as I go from A to B, the slopes of these tangent lines are all positive, at least in this picture. That's not the case in every concave up picture, but they're at least positive here. And not only that, but they're increasing, meaning they're getting steeper. So this tangent line is not very steep, but this one is steeper than the one that precedes it, and this one is steeper than the others that precede it. So what we're seeing is that the derivative of f is increasing on this interval because those slopes are getting larger, they're getting steeper. Similarly, over here on our concave down curve, the slopes of these tangent lines are starting steep near A, but getting less and less steep as we approach B. So the slopes are decreasing in this case. So if our slopes are increasing here and decreasing here, that's the same thing as saying that f prime is increasing here and decreasing here. But if f prime is increasing, then its derivative would be negative or positive. That's the correlation between an increasing function and its derivative. So since we're talking about the derivative of f prime, that's f double prime. And so what we conclude from this is that if f double prime is positive, then the original function f of x is concave up on whatever interval that second derivative remains positive. Similarly, if the second derivative of f, or we're calling it g in this example, but whatever you want to call it, if the second derivative is negative on an interval, that indicates that my graph is concave down on that interval. And again, that all just follows from the discussion we just had. So here's a summary of those concepts. This is exactly what I said. You have to assume f is twice differentiable on an interval before you can say this, because otherwise that second derivative wouldn't exist everywhere in that interval. But if that's the case, this is the way that we determine whether f is concave up or concave down. Okay? All right. Now, there are plenty of curves that you have seen already that have some intervals on which the curve is concave up and others on which it's concave down. So for this example right here, you can see that this first part of the curve up to this point appears concave down. It's kind of curving in a downward fashion. But then it's going to pass through this point and it's suddenly going to switch from being concave down to being concave up. So we had a change in concavity occurring there. On any function, on the graph of any function, if the function is continuous at a particular point where concavity changes as you pass that point, we call that a point of inflection. So that's going to be an important term in this section, point of inflection. And if you think about it, where would a point of inflection occur? Well, there's a couple of different possibilities for that, as we're going to see as we move on. In this case, the point of inflection would occur at a place where f double prime is equal to 0. Because if you think about it, if f double prime is negative, then we're still concave down at that point. If f double prime is positive, then we're concave up. So if we're at a point where there's a change in concavity, then that has to be a point where the curve is neither concave down nor concave up, just at that point though. So it could not be positive or negative. That means the second derivative could be 0. That's neither positive nor negative. Or the other possibility is that the second derivative might not exist there. We've seen examples where a function can be defined and continuous somewhere, but its derivative is not defined at that value. So if that happens with the second derivative, that's potential for a point of inflection. So because points of inflection give us the places where concavity changes, one of the things we're going to do in this section is try to use those points of inflection to find intervals on which concavity is changing. Now, concavity doesn't always have to change at a point of inflection. Sometimes you can get something like this. I can have a concave up part of my curve here, and then I can have a concave down part of my curve here. In fact, let me make that an open circle like that. If this is A, there is no point at A, so there's nothing that I could identify as a point of inflection. but we are experiencing a change from concave up to concave down there. So concavity doesn't always change at a point of inflection. That's only if concavity changes at a point where the curve is continuous. So to account for either of these situations, remember, if a function is not continuous somewhere, then it's also not differentiable there, and so it certainly wouldn't have a second derivative either. So that still falls under the category of the second derivative not existing. To summarize this, we define these things called partition numbers. Now, we've already seen partition numbers of f prime in the previous section. These are partition numbers of f double prime. And notice they're defined in a similar way. Partition numbers of f double prime are the x values for which f double prime either equals 0 or does not exist. So this almost feels the exact same as partition numbers of f prime, but the only difference is that these would be first derivatives instead of second derivatives in that case. We're going to use these for kind of the same basic idea, though. We want to find intervals of concavity and inflection points using these partition numbers. So here's kind of a step-by-step process. How do we find intervals of concavity, meaning on which intervals is a function concave up and which intervals is it concave down? How do we find inflection points using this thing that we call the concavity test? So first, we determine the domain of f. This is just like the increasing-decreasing test from the previous section. Then we find those partition numbers. Find all of the values for which your second derivative is either equal to 0 or does not exist. And then we create a sign chart. Now, I'm not going to go through the explanation of what a sign chart is because we did this in 3.1. But in this case, we're going to use the sign chart in basically the same way we did with the increasing-decreasing test and the first derivative test in the previous section, except we're using f double prime in that process instead of f prime. And the results of that sign test aren't going to tell us if the function is increasing or decreasing. It's going to tell us whether it's concave up or concave down. So let's see an example or two where we use this. I have a function here. I want to find the intervals of concavity and the points of inflection. So as before, we look at the domain of our function first. This is a polynomial. The domain of any polynomial is all real numbers. That doesn't really give us much useful information because the purpose of finding the domain is really to look more for where the function is not defined so that we account for that in our sign chart. But there's nothing to account for here. Next thing I want to do is find f double prime. Start with f prime. So that's going to give me 6x squared minus this guy here is going to give me 18x, and then that's going to give me plus 12. The minus 3 goes away, it's constant. And then find f double prime from that. So f double prime of x, again, is pretty straightforward. This is going to be 12x minus 18. That 12 goes to 0 as well. Okay? Now, the purpose of this was to look for partition numbers. Partition numbers, again, are anywhere where the second derivative of our function either is equal to 0 or does not exist. However, this is a polynomial in its own right, and again, remember, those polynomials have domains of all real numbers. So there is no value of x for which this is not defined. That means if I'm going to find a partition number, I'm only looking for where this is equal to 0. This is easy to solve. X would be equal to 3/2 in this case. I'm going to leave the algebra out because you should be able to fill in those gaps. So next thing I want to do is create a sign chart using my one partition number that I was able to find. 3/2. Okay, and we do what we did in the the first derivative test and the increasing-decreasing test back in 3.1. We pick test points. So for example, x equals 0, and we determine is f double prime positive or is it negative? Well, plugging a 0 into f double prime, not f prime, would give me negative 18. That's a negative number, so we have negative there. If I plug a test point in from this side, let's say x equals 10. Okay. Remember, we don't care what the exact value of f double prime is. We only care whether it's positive or negative. So plugging a 10 in for x here would give me 120 minus 18. 120 is much bigger than 18, so the subtraction should come out positive. I get a positive number from that. Okay, so looking at everything that we have here, I can determine where we have concavity, specifically where is our function concave up and concave down. Let's write those in. Where does this happen? Well, it's concave down where f double prime is negative, and that occurs here. So that corresponds to the interval from negative infinity to 3/2. Remember, open intervals, okay? Which means this other interval where f double prime is positive is where we have the function being concave up, 3/2 to infinity. Now, do we have a point of inflection? Yes, our point of inflection is going to occur when x is equal to 3/2. And I know this because the function changes concavity once we get past x equals 3/2. But then in addition to that, the function is continuous at 3/2 because, again, it's a polynomial. Polynomials are continuous everywhere. So a point of concavity is a point. It has an x and a y coordinate. This is just the x coordinate. I would need to find the y coordinate as well, f of 3/2. That's going to give me my y coordinate. So again, here's f up here. I did not work this one out ahead of time. I kind of wish I did, but that's okay. We're going to work this out together. So this is going to be 3/2 cubed minus 9 times 3/2 squared plus 12 times 3/2 minus 3. Okay, so I'm going to kind of work through some of this using a little bit of mental math. I would cube the 3 and the 2. 2 cubed is what I would get my denominator, but then I'm multiplying by another 2 here, so that would be 2 squared when the cancellation happens, giving me a 4 in my denominator. 3 cubed is equal to 27, so I'm going to have that. Here, I'm going to have 3 squared, which is 9, over 2 squared, which is 4, times this 9, so that 9 times this 9 would be 81 over 4. Some cancellation happens here. I'm going to get a 6 times 3, which is 18, minus 3, that would be 15. So plus 15. And then let's see, 27 minus 81 is negative 54 over 4 plus 15. And 15 is the same thing as 60 over 4. So when I add these, I'm going to get positive 6 over 4, or 3/2. So interestingly enough, the y coordinate comes out to the same thing as my x coordinate. Sorry, I didn't realize I was off screen that whole time. So the point of inflection is the point 3/2, 3/2. Now, I'll double check that later just in case I made an arithmetic mistake, but that's what we should be getting. Okay. I think what I'm going to do is, since this video is getting kind of long, I'm going to do the second part of this at the beginning of the next video.